begin. This video is a demonstration of how to solve problem VC_EC_2 by Martin Iduarte. First, we are given the following. G1 equals -4%, G2 equals +2%, and U equals 70 miles per hour. For our purposes, we will convert this into feet per second using the factor 1.47. Which gives us 103 feet per second. Using the aforementioned information, including several assumptions, we will determine the minimum length of the curve, the elevation y as a function of x, and number 3, calculate the high and low points. Let's begin. For determining the minimum length of the curve, we must first determine the stopping sight distance, SSD. This is the sum of the reaction distance and braking distance, RD and BD. Reaction distance is the product of the assumed constant design speed, U, and perception time, T. According to the 6th edition Highway Capacity Manual, 85% of drivers have a perception reaction time less than 2.5 seconds, which we will assume is sufficient for our calculation. The braking distance equation is derived from the constant acceleration kinematics equation. Change in v squared is equal to 2a change in x. On an incline where the acceleration is parallel to the slope, the normal force is perpendicular to the slope and gravity is perpendicular to the ground, or in this case, the datum. The manual also lets us assume a design braking deceleration of a is equal to 11.2 feet per second per second. For our friction constant F, we will use A over G. The acceleration due to gravity of 32.2 feet per second per second excuse me, giving us an F of 0.348. Excuse me. And for our purposes, G will equal 0. Therefore, our braking distance, U squared over 2G, F plus G, will be plugged in to our total SSD equation. Let's see. SSD equals 103 FPS times 2.5 seconds plus 103 feet per second squared divided by 2 times 32.2 feet per second times 348 plus 0, which equals 728 feet. That's our stopping sight distance. On sag curves, stopping sight distance is the light beam distance from the driver's eye at height H1 above the PVC, and slope G1 to the bottom of the car H2 above the PVT on a slope G2, where the headlight beam diverges by beta degrees. We assume that the driver's eye is 3.5 feet above the road, and that the second height is 0 feet above the road, and beta is equal to 1 degree. We must assume either that the length is less than the stopping sight distance or the length is greater than the stopping sight distance. For that, we have two equations. SSD is less than L, and SSD is greater than L, where L equals, if SSD is less than L, A times SSD squared over 200 H1 plus S tan beta. And here, L is equal to 2 SSD minus 200 H1 plus SSD tan beta over A, where these two simplify to ASSD squared over 400 plus 3.5 SSD. And here, L equals 2 SSD minus 400 plus 3.5 SSD over A. Plugging in for each assumption, we get L equals 6 times 728 squared over 400 plus 3.5 times 728, which gives us 1079 feet. Here, when SSD is greater than L, we have 2 times 728 minus 400 plus 3.5 times 728 over 6, which equals 965 feet. Let's move to the next page for some more space. For our first assumption, SSD is less than L, we have 728 is less than 1079, which is true. For our second assumption, we have SSD is greater than L, but we have 728 is not greater than 965. So this assumption is not true. Okay. Now that we have our L, our second part is to find the function y of x. We will be using the quadratic equation y is equal to ax squared plus bx plus c, where a equals the change in grade over 2L, b equals the first grade, and c equals the elevation at the vertical curve. For our purposes, this will be 0, meaning our function will tell us our vertical distance from the PVC. Our G1 is negative 4x 10 to the negative 2. Our A is 2, let's see here. I'm slowing down. My bad. It's 0.02 minus negative 0.04 over 2 times 1078, which equals 2.78x 10 to the negative 5. Very small number. We have our A, we have our B, and our C. That means our function is y is equal to 2.78x 10 to the negative 5x squared plus 4x 10 to the negative 2x. Finally, we want to find our high points and low points. We want to find our low point here, and either one of these is going to be our high point. Since our quadratic equation is just like any other parabola, we'll use the x of the low point is equal to b over 2a, which equals to 4x 10 to the negative 2 over 2 times 2.78 is 10 to the negative 5, which equals 719 feet into the curve. Since we're calling the station our origin, we could say this is station 7 plus 19. Anyways, to find the height of our low point, we put the function of 719 gives us negative 14 feet. That's our low point from the PBC. Our f of 0 equals 0, and our f of L, this is our L, equals x equals 7 to 8. Plugged in gives us negative 11 feet. Negative 11 feet here, and 0 feet here. This is our high point. This is our low point. We have answered all three objectives. That concludes the problem.